Standing in the shadow of a towering ancient pyramid, or gazing up at a gargantuan stone wall carved with impossible precision, it's hard not to wonder, how did they do it? Long before cranes, lasers, or computer-aided design, civilizations around the world achieved engineering feats that still leave experts scratching their heads. These weren't just buildings, they were declarations of human ingenuity, testaments to what's possible when creativity meets sheer determination. And the most astonishing part: many of these structures were built with nothing more than primitive tools, ropes, and an unwavering vision that defied the limits of their time. Take a moment to picture it. Thousands of workers hauling multi-ton stones across deserts, forests, and mountains, aligning them with celestial precision, often without written language or modern mathematics to guide them. Some of these megastructures were so advanced, so perfectly engineered, that even today we struggle to replicate their techniques. From the labyrinthine tunnels beneath Egypt to the floating temples of Cambodia, each one whispers secrets of lost knowledge, methods so effective that they've stood for thousands of years, outlasting empires and weathering countless storms. This is a journey into the impossible. Across continents and centuries, we'll uncover 30 ancient marvels that shouldn't exist, yet somehow do. These aren't just relics of the past, they're puzzles waiting to be solved, challenges to everything we think we know about early civilizations. How did they move stones heavier than elephants? How did they achieve alignments with the stars using only the naked eye? And why, despite all our advancements, do their techniques remain shrouded in mystery? The answers might surprise you, because when it comes to the ancient world, the line between myth and reality is thinner than you think. So let's step into the footsteps of the builders, the dreamers, and the innovators who left behind a legacy carved in stone. Their stories are waiting. The Great Pyramid of Giza doesn't just dominate the Egyptian desert, it defies logic. Built over 4,500 years ago with an estimated 2,300,000 stone blocks, each weighing as much as 2.5 elephants, this ancient marvel wasn't just stacked, it was engineered with near impossible precision. The four sides align almost perfectly with the cardinal directions, deviating by less than a fraction of a degree, a feat that would be impressive even with today's satellite technology. But here's the real mystery. How did a civilization without compasses, cranes, or computers achieve such accuracy? Some theories suggest massive ramps spiraled around the pyramid, allowing workers to drag blocks upward. Others propose internal ramps hidden within the structure itself, a secret network of passageways that made the impossible possible. Yet no single explanation fully accounts for the pyramid's flawless symmetry or the speed of its construction. The stones fit so tightly that not even a sheet of paper could slide between them, no mortar, just perfect cuts and angles that have withstood millennia of earthquakes and erosion. Even more astonishing is its celestial connection. The pyramid's shafts align with specific stars, mirroring the night sky as it appeared in ancient times. Was this a cosmic blueprint, a way to link the pharaoh's journey to the afterlife with the heavens? Or was it a display of mathematical genius encoded with secrets we're only beginning to decode? Modern engineers still debate whether we could replicate this precision today, even with lasers and software. That's the true wonder of the Great Pyramid. It wasn't just built to last. It was built to leave us questioning everything we know about the past. From the Egyptian desert to the misty plains of England, another ancient marvel stands shrouded in mystery: Stonehenge. This ring of towering stones, some weighing as much as 25 tons, wasn't just dropped into place by chance. Neolithic builders somehow dragged these monoliths over 20 miles across rugged terrain without wheels or pack animals. The logistics alone boggle the mind. How did they move slabs heavier than a school bus using nothing but brute strength and primitive tools? Theories abound. Some suggest they slid the stones on wooden sledges greased with animal fat, leveraging the slick surface to reduce friction. others propose a system of rollers, tree trunks laid end to end like a makeshift conveyor belt, with teams of workers heaving the stones forward inch by painstaking inch. But even these explanations leave gaps. How did they lift the massive lintels, the horizontal stones perched precisely atop the vertical ones, without cranes or pulleys? Experiments with replica stones and ancient techniques have shown it's possible, but the margin for error was razor thin. One misstep, and the whole structure could have come crashing down. Yet Stonehenge wasn't just a feat of engineering, it was a celestial calculator. The stones align with the summer and winter solstices, marking the sun's furthest points in the sky with eerie accuracy. During the summer solstice, the rising sun pierces perfectly through the heel stone, casting a beam directly into the heart of the circle. Was this a Neolithic calendar, a temple for sun worship, or something even more profound? The builders left no written records, only silent stones that whisper of a deep understanding of the cosmos. What's truly humbling is the scale of cooperation this must have required. Stonehenge wasn't built in a year or even a generation. It evolved over centuries, with each new phase demanding meticulous planning and communal effort. This wasn't the work of a handful of people. It was a societal undertaking, a testament to what humans can achieve when united by a shared vision. And perhaps that's the greatest mystery of all, not just how they moved the stones, but why they went to such extraordinary lengths to do so. Even today, as lasers scan the site for hidden clues and archaeologists debate its purpose, Stonehenge refuses to give up all its secrets. It stands as a silent challenge to our assumptions about primitive societies, reminding us that the past is far more sophisticated than we often give it credit for. The stones don't just mark a spot on the landscape, they mark a moment in human history where ambition, astronomy, and sheer willpower converge to create something timeless. High above the clouds, nestled between jagged Andean peaks, Machu Picchu clings to the mountainside like a puzzle assembled by the gods themselves. What makes this Incan citadel so extraordinary isn't just its breathtaking location, it's the stonework. Walls built without mortar, where massive rocks lock together so precisely that not even a razor blade could slip between them. These aren't just stacked stones, they're masterpieces of engineering, shaped and placed with such care that they've withstood centuries of earthquakes, landslides, and torrential rains. The Incas worked with a material older than their civilization, granite, one of the hardest stones on Earth. Yet with nothing but bronze tools, wooden levers, and an intimate understanding of geology, they transformed raw boulders into perfectly fitted blocks. Imagine the process: laborers chiseling away at quarries miles from the construction site, using hammerstones to fracture the rock along natural fault lines. Once freed, these multi-ton stones were dragged along steep mountain trails, likely on log rollers or sledges, with teams of workers pulling ropes in unison. The terrain alone would have been a nightmare: narrow paths, sheer drop-offs, and unpredictable weather. But the Incas didn't just move these stones, they perfected them. Each block was painstakingly shaped by abrasion, rubbed against other stones until their surfaces matched like interlocking pieces. The result: walls that curve and lean organically, yet never lose their structural integrity. Some stones have as many as 30 angles, all cut to nestle seamlessly against their neighbors. This technique, called ashlar masonry, wasn't just about aesthetics, it was survival. In a region prone to violent tremors, mortar would have crumbled, but these precisely fitted stones could shift and settle during quakes, then settle back into place like a self-healing structure. Even more baffling is how they achieved such precision without modern measuring tools. Some researchers believe the Incas used simple yet ingenious methods, pouring water over stones to trace uneven spots or using knotted strings to gauge distances. Others speculate they employed templates, carving grooves into softer rocks to guide their chisels, but the truth is we still don't know for certain. What's clear is that this wasn't haphazard labor, it was a refined craft passed down through generations, Machu Picchu wasn't just a fortress or a temple, it was a testament to harmony. The stones mirror the contours of the mountains, blending into the landscape as if they'd always been there. And perhaps that's the most humbling lesson of all. In a world obsessed with speed and force, the Incas remind us that patience, precision, and respect for nature's design can create something truly eternal. Their walls don't just stand, they sing. Easter Island's Moai statues stand like silent sentinels, their massive stone faces gazing inland as if guarding secrets lost to time. Each one weighs as much as 10 elephants, some tipping the scales at 80 tons, and yet, centuries ago, the Rapa Nui people not only carved these colossal figures from solid volcanic rock, but transported them miles across rugged terrain without wheels, beasts of burden, or metal tools. The question isn't just how they did it, it's why they went to such extraordinary lengths. Carving the moai was a feat of patience and precision. Using basalt hand chisels, workers painstakingly shaped the statues directly from the walls of Raraku, the island's volcanic quarry. The softer rock allowed for detailed facial features, arched brows, sharp noses, elongated ears. Each chisel stroke a testament to artistry passed down through generations. But the real challenge began once the statues were freed from the earth. How do you move an 80-ton block of stone across hills, ravines, and uneven ground? For years, the popular theory claimed the moai walked to their final positions, rocked side to side by teams pulling ropes, a dramatic idea popularized by modern experiments. But archaeology tells a different story. The island's ancient paths, littered with broken and abandoned moai, suggest a far more practical method: sledges and log rollers. The Rapa Nui likely leveraged the island's once thick palm forests, felling trees to create makeshift tracks. Teams would have hauled the statues atop wooden sledges, greased with sweet potato paste to reduce friction, while others placed rollers ahead to keep the momentum going. It wasn't magic, it was physics, teamwork, and sheer determination. Yet the environmental cost was staggering. The very forests that provided the logs for transportation were eventually depleted, a cautionary tale of resource management. But in their prime, these methods worked. Once the moai reached their ceremonial platforms, or ahu, the final step was even more audacious: erecting them. Using ramps and lever systems, crews would have painstakingly tilted each statue upright, securing it to the platform with stone rubble. Some moai even wore red stone hats called pukao, quarried from a different site, proof that the Rapa Nui's engineering ambition knew no bounds. What's often overlooked is the cultural drive behind this effort. These weren't just statues, they were vessels of ancestral energy, believed to watch over the living. The moai's backs are carved with intricate petroglyphs, their faces oriented to shelter villages, a spiritual covenant etched in stone. When European explorers arrived in the 18th century, they found most moai toppled, likely from tribal conflicts or environmental collapse. But the statue's silent endurance speaks volumes. Today, as researchers use 3D imaging to study tool marks and soil erosion patterns, the moai remind us that human ingenuity thrives even in isolation. The real marvel isn't just the engineering, it's the audacity. On a remote island with no outside influence, the Rapa Nui devised solutions that rival the pyramids or Machu Picchu. Their story isn't one of mystery but of adaptability, a testament to what happens when culture, faith, and resourcefulness collide. And perhaps that's the moai's quiet lesson: monuments aren't just made of stone. They're made of the will to create something greater than ourselves. Rising from the valley floor like a man-made mountain, Teotihuacan's Pyramid of the Sun dominates the ancient cityscape with quiet authority. Built around 2,000 years ago by a civilization so enigmatic that we don't even know what they called themselves, this colossal structure wasn't just stacked, it was woven into the fabric of the cosmos. Standing over 200 feet tall with a base nearly as wide as the Great Pyramid of Giza, its sheer scale is staggering. But the real genius lies in how it was built, without metal tools, wheels, or even written records to guide the hands of its creators. The pyramid's construction reveals layer upon layer of intention. Unlike the smooth-sided pyramids of Egypt, this was a stepped structure, each tier meticulously filled with rubble and earth, then faced with locally quarried volcanic stone. Workers hauled millions of tons of material, some stones weighing up to 20 tons using nothing but rope, wooden sledges, and raw manpower. The logistics were mind-bending. Without pack animals or carts, teams would have dragged stones along dirt roads softened with water to reduce friction, leveraging the valley's natural slopes to minimize effort. But the precision didn't stop there. The pyramid's alignment is no accident. It faces directly toward the setting sun on key dates in the Mesoamerican calendar, a celestial handshake between earth and sky. Beneath this monumental facade lies another mystery, a labyrinth of tunnels. In the 1970s, archaeologists discovered a cave-like passage running hundreds of feet beneath the pyramid, echoing the shape of a flower with petals, a design mirrored in later Aztec cosmology. Was this a sacred pathway to the underworld, a repository for ritual offerings? The tunnel's walls bear traces of mercury and other rare minerals, hinting at ceremonies we can only guess at. Even more perplexing is how these passages were dug without collapsing, using only wooden supports and stone tools to carve through unstable volcanic soil. What truly sets Teotihuacan apart is its harmony with the landscape. The pyramid isn't just placed on the ground, it's integrated. The builders used the natural contours of the Cerro Gordo mountain to amplify the structure's presence, creating an illusion that it's emerging from the earth itself. Nearby, the Street of the Dead stretches like a perfect north-south axis, flanked by smaller pyramids and platforms, all aligned with celestial events. This wasn't haphazard urban planning. It was a three-dimensional map of the universe, a place where every stone whispered of sacred geometry. The absence of any known writing system at Teotihuacan only deepens the wonder. How did they communicate such complex engineering plans? How did they pass down knowledge across generations without written records? Some researchers believe they used oral traditions and physical models, perhaps shaping clay or sand to demonstrate designs. Others point to the city's standardized construction modules, consistent measurements repeated across buildings suggesting a shared architectural language. Standing atop the Pyramid of the Sun today, it's hard not to feel the weight of its silence. The civilization that built it left no kings' names, no battle chronicles, just stones that hum with intention. Modern laser scans reveal hidden chambers still untouched, promising more secrets, but perhaps the greatest lesson isn't in how they built it, but why. In a world without modern technology, they reached for the sky anyway, crafting a monument that would outlast their memory. That's the paradox of Teotihuacan, a city built by the unknown for the unknown, yet standing as one of humanity's most enduring conversations with time. Göbekli Tepe shatters every assumption we have about early human societies. This ancient temple complex, carved from limestone over 12,000 years ago, predates the invention of agriculture by millennia, proof that hunter-gatherers accomplished engineering feats rivaling later civilizations. Picture this: circular enclosures filled with towering T-shaped pillars, some standing 16 feet tall and weighing up to 20 tons, each meticulously carved with intricate animal reliefs. The implications are staggering. How did nomadic peoples without permanent settlements or metal tools quarry, sculpt, and erect these monoliths using nothing but flint chisels and sheer manpower? The site's construction defies logic. Workers would have extracted massive limestone blocks from nearby quarries using primitive wedges and hammerstones, then painstakingly shaped them into smooth pillars. But the real challenge was transport. Without wheels or domesticated animals, moving these megaliths even short distances would have required coordinated effort. Hundreds of people pulling ropes, likely rolling the stones on logs or dragging them over greased clay paths. What's even more baffling is the precision. The pillars fit into sockets carved into the bedrock, their positions revealing an understanding of weight distribution and stability that feels impossibly advanced for its time. Göbekli Tepe's artistry is equally mesmerizing. The pillars aren't blank monoliths, they're canvases. Foxes, scorpions, and vultures slither and swoop across the stone, their forms etched with a clarity that suggests generations of artistic tradition. Some researchers believe these carvings weren't just decoration, but a form of communication, a symbolic language predating writing. The animals might represent constellations, clan totems, or even early deities, hinting at a spiritual sophistication we rarely attribute to hunter-gatherers. The timeline here is what truly upends history. Conventional wisdom says humans built temples after settling into farming communities, when surplus food allowed for specialized labor. But Göbekli Tepe flips that narrative. Here, monumental architecture came first, implying that communal ritual, not just survival, drove innovation. Perhaps it was the need to feed workers building these shrines that spurred early experiments with cultivating wild grains. In other words, religion might have birthed agriculture, not the other way around. Even the site's deliberate burial adds to the intrigue. Around 8,000 years ago, someone carefully buried Göbekli Tepe under thousands of tons of earth, preserving it like a time capsule. Was this an act of reverence, or were they hiding knowledge too potent to leave exposed? Modern archaeologists, armed with ground-penetrating radar, estimate less than 10% of the site has been uncovered. Every new excavation reveals more pillars, more enclosures, each layer older than the last. Standing amid these ruins, you're left with a humbling realization. Our ancestors were far more than mere survivors. They were visionaries who reshaped the world with flint and sweat, driven by something deeper than necessity. Göbekli Tepe doesn't just rewrite history, it dares us to reconsider what humans are capable of when imagination, not just invention, leads the way. Baalbek's Trilithon stones defy belief, even in the shadow of Rome's greatest engineering feats. These three colossal blocks, each weighing nearly 800 tons, equivalent to two fully loaded jumbo jets, form the foundation of Jupiter's temple in modern-day Lebanon. Their precision placement, locked together seamlessly at a height of 20 feet above ground, poses a question that's haunted archaeologists for centuries. How did Roman engineers move and lift the heaviest freestanding stones ever used in construction? The logistics are mind-bending. Quarried over half a mile from the temple site, the limestone monoliths were extracted with nothing but wooden wedges and bronze tools. Workers would have soaked the wedges in water, letting the expanding wood fracture the bedrock along natural fissures, but freeing the stones was just the beginning. Transporting them required a feat of collective ingenuity. Unlike Egypt's sandy plains or Easter Island's rolling hills, Baalbek's terrain is rugged, forcing engineers to devise custom solutions. The most plausible theory involves a combination of levers, rollers, and earthen ramps, a system where hundreds of laborers pulled ropes in unison, while others placed wooden rollers beneath the stones, greased with olive oil to reduce friction. Yet the real marvel lies in the lifting. Without hydraulic cranes, the Romans likely built massive earthen ramps, packing layers of soil and rubble to create temporary inclines that reached the temple's foundation height. Teams would have painstakingly dragged each stone up these slopes, adjusting its position with wooden levers. Once aligned, the ramp material was gradually removed, lowering the block into place with terrifying precision. One misstep could have shattered the stone or crushed workers, yet the Trilithon's flawless placement suggests near-perfect execution. What's often overlooked is the cultural audacity behind this effort. These weren't merely foundation stones, they were a statement. Roman occupation demanded visual dominance, and the Trilithon's scale, visible from miles away, served as psychological warfare, proclaiming imperial power through sheer mass. Modern engineers have attempted replicas using Roman-era techniques, only to abandon projects midway, realizing the sheer physical toll. But the mystery deepens beneath the temple. Recent ground-penetrating radar revealed a fourth block, larger than the Trilithon, left in the quarry. Dubbed the Stone of the Pregnant Woman, this 2,100-ton behemoth suggests the Romans aimed for something even grander before conceding to logistical limits. Its abandoned state offers a rare glimpse into ancient ambition, a reminder that even history's greatest builders sometimes met their match. Standing before these stones today, you're not just seeing engineering, you're witnessing a dialogue between human will and physical law. The Trilithon doesn't just support a temple, it supports the idea that with enough collaboration, creativity, and raw determination, the impossible is just another problem waiting to be solved. And perhaps that's why, 2,000 years later, we still crane our necks upward, marveling not just at how they did it, but why they believed they could. The Parthenon's gleaming marble columns rise against the Athenian sky not as rigid lines, but as living geometry, a masterclass in deception and precision. At first glance, the temple appears perfectly rectilinear, but every measurement is a carefully crafted illusion. The columns bulge slightly at their centers, a technique called intosses, counteracting the optical distortion that makes straight columns appear pinched to the human eye. Even the temple's base curves upward at the center, creating the impression of flawless flatness against the horizon. This wasn't just architecture, it was psychology in stone, designed to trick the brain into seeing perfection where none exists naturally. Carving these optical feats required more than artistry, it demanded revolutionary engineering. Each of the Parthenon's 46 columns was assembled from 11 precisely drum-shaped marble segments, quarried from Mount Pentelicus over 10 miles away. Without modern saws or drills, workers extracted the marble using wooden wedges hammered into natural fissures, then split the rock with startling accuracy. Transporting these multi-ton blocks to the Acropolis would have been a Herculean task. Teams likely rolled them on wooden sledges along a road lubricated with olive oil, a slick surface reducing friction enough to move what brute strength alone couldn't budge. But the real magic happened during assembly. To hoist the massive drums into place, Greek engineers employed an array of bronze pulleys and hemp ropes, some as thick as a man's arm, anchored to wooden cranes. Workers would have leveraged counterweights and capstans, winding the ropes through systems so efficient that a single team could lift a 5-ton segment into position. The final touch, each column's segments were pinned together with iron clamps set into molten lead, a technique that allowed for slight movement during earthquakes without collapsing. The Parthenon's precision goes beyond mere survival. Its dimensions encode mathematical harmonies, with ratios mirroring those found in nature column spacings based on the golden mean, proportions echoing musical intervals. Some researchers believe the temple's layout could function as a giant sundial, its shadows marking solstices and equinoxes with uncanny accuracy. Even the sculptural decorations played a role. The metopes and frieze weren't just art but counterweights, their distribution balancing the structure against wind and tremors. What's most humbling is the timeline. The entire Parthenon was erected in just 9 years, a blink compared to centuries-long projects like the pyramids. This speed speaks to an organized society where architects, stonemasons, and laborers shared a unified vision. They didn't just build a temple, they engineered a symphony in marble where every optical trick, every hidden curve served a singular purpose: to make the human eye believe in the impossible. Today, even eroded and battle-scarred, the Parthenon still achieves that goal. Its columns don't just stand, they dance. Rome's Colosseum wasn't just an amphitheater, it was a revolution in stone and sweat. Imagine 50,000 spectators roaring under a blazing sun, their voices echoing through a maze of vaults and arches that defied gravity with nothing but geometry and clever engineering. Built in just 8 years with no cranes, no steel, and no concrete mixers, this iconic structure relied on 2 secret weapons: travertine limestone and an innovative recipe for Roman concrete so durable it's still studied by engineers today. The construction process was a ballet of brute force and precision. Workers quarried travertine blocks from mines over 20 miles away, each weighing up to 5 tons. Without diesel trucks, they relied on ox-drawn carts and a network of purpose-built roads, hauling stones to the site where teams shaped them with iron chisels. But the real magic lay in the Colosseum's skeleton, a lattice of arches stacked like a honeycomb. These weren't just decorative, they distributed weight so efficiently that the structure could support its own massive scale while using far less material than solid walls. Roman concrete played a starring role. Unlike modern concrete, which weakens over time, theirs grew stronger. The secret volcanic ash from Mount Vesuvius mixed with lime and seawater to create a chemical reaction that formed ultra-resistant minerals. This pozzolana concrete filled the vaults, setting quickly even underwater, a feature that allowed builders to work at unprecedented speeds. The amphitheater's elliptical shape wasn't just for aesthetics, it maximized sight lines and crowd flow. Beneath the arena floor, a labyrinth of tunnels and elevators powered by capstans and counterweights allowed gladiators and wild beasts to emerge dramatically through trapdoors. The entire system operated without a single motor, just pulley systems and enslaved labor, a sobering reminder of the human cost behind ancient engineering feats. What's often overlooked is the Colosseum's adaptability. Its 80 entrances, called vomitoria, could empty the entire structure in minutes, a crowd control innovation still echoed in modern stadiums. And the retractable velarium, a massive awning shading spectators, required a small army of sailors to maneuver ropes anchored to stone corbels. Standing in the ruins today, the genius is palpable. The arches that framed every gladiator's entrance, the concrete that outlasted empires, the sheer audacity of building something so colossal with hands and rudimentary tools, it all whispers the same truth: the Romans didn't just construct. They engineered for eternity, and 2,000 years later, as tourists trace their fingers over pockmarked travertine, the Colosseum still delivers on that promise. Angkor Wat rises from the Cambodian jungle like a mirage of sandstone and spirituality, its 5 iconic towers mirrored in still waters as if floating between earth and sky. But this architectural masterpiece, built in the 12th century, hides an engineering puzzle beneath its serene surface. Each block of sandstone, millions of them, was quarried from Mount Kulin, a grueling 25-mile journey through dense rainforest and swampy terrain. No wheels, no carts, just elephants, ropes, and the sweat of thousands of workers who turned an impossible logistics nightmare into reality. The quarrying process alone was a feat of precision. Workers used iron chisels to carve deep grooves into the sandstone bedrock, then hammered wooden wedges into the fissures. When soaked with water, the expanding would split the stone cleanly along natural fault lines, yielding blocks that could weigh up to 2 tons. But extracting the stones was the easy part. Transporting them through mosquito-infested jungles and across unpredictable rivers required ingenuity on a grand scale. Historians believe the Khmer engineers built an intricate network of canals, using the region's seasonal floods to their advantage. During the monsoon, workers loaded stones onto bamboo rafts, letting the swollen currents carry them partway to the site. When the waters receded, elephants took over, their immense strength harnessed to drag stones the final miles over temporary causeways of packed earth and palm logs. Assembly was another marvel. Without cranes, the Khmer relied on a combination of inclined earthen ramps, wooden scaffolding, and rudimentary pulley systems. Workers would have stacked blocks layer by layer, each core slightly recessed to create internal terraces that served as platforms for the next phase. The towers themselves were built using a false arch technique, each level cantilevered outward until meeting at the peak, a method demanding millimeter-perfect precision to avoid collapse. Some scholars argue the entire complex was constructed from the top down, with crews building temporary wooden structures to support upper levels before completing lower walls, an approach as audacious as it was risky. What's often overlooked is Angkor Wat's celestial alignment. The temple's central axis points almost precisely west, aligning with the spring equinox in a way that makes the sun appear to crown the central tower at dawn. This wasn't accidental. Khmer astronomers likely used simple tools like Naman poles and water clocks to track solar movements, embedding astronomical knowledge into the very stones. Even more astounding are the bas-reliefs stretching nearly half a mile in total length, depicting Hindu epics with such detail that individual feathers on carved birds remain visible. Artists would have worked by oil lamp in windowless galleries, their chisels guided by generations of inherited technique. But the true wonder isn't just how Angkor Wat was built, it's how it endured. Unlike mortar-bound structures that crumble over time, the Khmer used a gravity-fit system where each block's weight locks it into place. During earthquakes, the stones shift slightly before settling back, a self-stabilizing design modern engineers call dynamic equilibrium. Even the moat plays a role, acting as a hydraulic buffer that stabilizes the sandy soil beneath the temple's massive weight. Standing in the pre-dawn darkness, watching the first light gild those ancient towers, you realize Angkor Wat isn't just a building. It's a testament to what happens when human ambition harmonizes with nature rather than conquering it. The Khmer didn't fight their environment, they listened to it, learned from it, and let it carry their stones to the sky. 9 centuries later, as moss creeps over carved devotas and roots weave through sandstone galleries, the temple still whispers its lesson. The greatest monuments aren't built against the world, but with it. Tikal's temples pierce the Guatemalan jungle canopy like stone mountains. Their stepped silhouettes a testament to Maya ingenuity in one of Earth's most unforgiving environments. Unlike the desert-bleached pyramids of Egypt or the windswept monoliths of Easter Island, these structures rose from a world of tangled vines, torrential rains, and soil that swallowed footprints whole. The Maya didn't just build here, they conquered the landscape itself, transforming swampy lowlands into a celestial metropolis with nothing but limestone, lime mortar, and an intimate understanding of their environment. The raw materials alone posed a monumental challenge. Every block of limestone was quarried from local bedrock using stone tools, obsidian chisels, and basalt hammers, then shaped with astonishing precision. But how do you move multi-ton stones through dense rainforest without wheels, metal tools, or domesticated animals? The Maya's solution was as elegant as it was labor-intensive, a network of sakbiab or white roads. These raised causeways, paved with crushed limestone and packed earth, served as both transportation routes and sacred pathways. Teams of workers would have hauled stones on wooden sledges, likely lubricated with water or plant sap to reduce friction, while others cleared vegetation ahead. The humid air and muddy ground made every footstep a battle, yet the Maya moved millions of cubic feet of stone this way. Even more impressive was their mortar. Unlike modern cement, Maya lime plaster was cooked in massive kilns at temperatures exceeding 1,000 degrees Fahrenheit, a process requiring thousands of carefully managed fires. Workers mixed the resulting quicklime with water and tree sap to create a paste so durable it still binds Tikal stones today. The secret lay in their chemistry. By adding organic compounds, they created a self-healing material that absorbed carbon dioxide over time, actually strengthening with age. The logistics of construction were equally brilliant. Instead of building from the ground up, the Maya often constructed new temples over older ones, layering pyramids like nesting dolls. This wasn't just practical, it was deeply symbolic, reflecting their belief in cyclical time. Scaffolding was made from guano wood lashed together with vines, while ramps of compacted rubble allowed workers to reach higher levels. At Tikal's Temple Roman IV, the tallest pre-Columbian structure in the Americas, engineers deliberately angled walls inward to counterbalance the jungle's unstable soil, a technique later rediscovered by modern skyscraper builders. But the true marvel was their celestial alignment. Every major temple at Tikal corresponds to astronomical events. During equinoxes, shadows slither down Temple I's northern staircase like a descending serpent mirroring Maya myth. This precision required generations of naked-eye astronomical observation, with architects using simple sighting tubes to track stars and align buildings accordingly. Standing atop Temple Roman 4 today, gazing over a sea of emerald treetops, you realize the Maya didn't just adapt to their environment, they choreographed with it. Their pyramids weren't just buildings, they were bridges between earth and sky, built by hands that turned jungle obstacles into tools. And perhaps that's their enduring lesson. Greatness isn't about conquering nature, but harmonizing with it so completely that stone seems to grow from the soil itself. Persepolis stands as a symphony in stone, where every chisel mark whispers of an empire's might. At its height, this ceremonial capital of the Achaemenid Persian Empire dazzled visitors with towering columns and walls adorned by thousands of intricately carved figures, each one shaped with nothing but bronze tools and an artist's unwavering patience. The scale is staggering, over 72-foot-tall columns supporting cedar beams hauled from Lebanon, stairways decorated with endless processions of tribute bearers, and doorways framed by colossal winged bulls. Yet beneath this grandeur lies a startling paradox. How did a civilization that mastered such delicate artistry also move and erect stones weighing multiple tons without pulleys or cranes? The answer lies in the perfect marriage of brute strength and refined technique. Take those iconic columns, for instance. Workers quarried limestone blocks from nearby Mount Romat using bronze chisels and fire setting, a method where they'd heat the rock face with fires, then douse it with water to cause thermal fractures. Once freed, these multi-ton segments were transported on a specially constructed road network, likely rolled on wooden cylinders greased with bitumen from natural seepage. But the real innovation came during assembly. Instead of lifting entire columns, Persian engineers built them in stacked segments, each drum precision carved with concave bases and convex tops to interlock like puzzle pieces. Teams would lever each section into place using wooden cranes powered by human counterweights, hundreds of laborers pulling ropes in unison from ramps that spiraled upward as the column grew. Now consider the reliefs, those mesmerizing panels lining the Apadana stairway, where delegates from 23 subject nations parade eternally in stone. Artisans worked with nothing but bronze picks and abrasives like powdered quartz, yet achieved details so fine they captured the texture of Babylonian wool and the intricate braids of Sogdian ambassadors. Some panels contain over 100 figures, each one unique, their robes and gifts rendered with photographic precision. The secret, a guild system where master carvers supervised teams of apprentices, each specializing in specific elements, one group for faces, another for textiles, ensuring consistency across thousands of square feet of artwork. The logistics behind Persepolis reveal an empire that thought in multiples. When King Darius ordered his palace built, he didn't just commission one structure, he engineered an entire prefabricated city. Columns were standardized in 20-foot segments for easy transport and assembly. Doorjambs were carved off-site with slots ready to receive hinge mechanisms. Even the famed griffin-headed capitals were designed in modular sections, allowing them to be hoisted and secured piece by piece. This wasn't just construction, it was early mass production, a system where every element could be replicated across an empire stretching from the Nile to the Indus. Perhaps most telling is what the stones don't show. Unlike Egyptian or Mesopotamian monuments plastered with boasts of royal conquests, Persepolis reliefs emphasize harmony, tribute bearers presenting gifts, not prisoners in chains. The message was clear. This wasn't a kingdom built on fear, but on the collective labor of diverse cultures. That collaborative spirit extended to the workforce. Clay tablets from the site list payments to artisans of various nationalities, proving the Persians didn't rely on slave labor but on skilled, compensated craftsmen. Today, as sunlight slants through the columns' remnants, casting long shadows over those silent processions, Persepolis still radiates its original intent. This wasn't merely a palace, it was a theater of soft power where architecture and artistry merged to awe visitors into loyalty, and in that the Persians succeeded beyond measure. Long after their empire faded, the stones still speak not of conquest, but of the enduring power of beauty, precision, and ambition carved patiently into the bones of the earth. Crouched on the hills above Cusco, Sacsayhuaman's jagged walls carve through the Andes like the teeth of a stone giant. These zigzagging battlements, built by the Incas in the 15th century, aren't just imposing, they're impossible. Stones weighing up to 120 tons are stacked in a jigsaw pattern so precise that even today, 500 years later, not a single blade of grass can wedge between them. No mortar, no gaps, just seamless fits that mock modern understanding. How did a civilization without iron tools or the wheel achieve such flawless masonry? The answers might lie in a combination of geology, ingenuity, and a philosophy that saw stone not as dead matter, but as something almost alive. Start with the stones themselves, andesite and diorite, some of the hardest rocks on Earth. Inca stonemasons didn't carve these blocks with chisels, they negotiated with them. Using hammerstones of even harder material, they pounded strategic grooves into the rock, then levered fractures along natural fault lines with wooden wedges soaked in water. The expansion would split the stone cleanly, like cracking an egg along its seam, but shaping was only half the battle. Transporting these megaliths from quarries miles away required a symphony of coordination. Without wheels or draft animals, teams likely slid stones on log rollers, maneuvering them up earthen ramps with ropes woven from iku grass, fibers so strong they could suspend bridges across canyons. The real genius, though, was in the fitting. The Incas didn't just stack stones, they dressed them, grinding each block against its neighbor using sand and water as abrasives until the surfaces matched perfectly. Some theories suggest they used clay molds to map out irregularities, pressing wet clay into gaps to identify high spots, then painstakingly grinding those areas down. Others propose they employed a system of knotted strings to measure and align angles, early geometry in action. The result, walls that curve organically yet lock together with unshakable stability, their zigzag design dispersing seismic energy like a crumple zone in a modern building. But here's what truly baffles engineers. Many stones have as many as 12 angles, each one precisely interlocking with its neighbors like a three-dimensional puzzle. This wasn't just craftsmanship, it was computational thinking without computers. Contemporary builders often attribute such precision to trial and error, but the Incas couldn't afford errors. Every misaligned block meant weeks of rework. More likely, they used scale models in clay or sand, testing fits before committing to stone. And then there's the purpose. While Spanish invaders assumed it was a fortress, recent archaeology hints at something grander, a ceremonial complex where the zigzag walls mirrored lightning bolts, sacred to the Inca sky god Elapa. Standing before these walls today, you're left with two irreconcilable truths. The Incas achieved this with nothing but stone, rope, and patience, yet part of you refuses to believe it. Maybe that's the point. Sacsayhuaman isn't just a ruin, it's a riddle carved in rock, daring us to reconsider what's possible when human hands work in harmony with the earth's bones. The stones don't just fit together, they conspire, hiding their secrets in plain sight. Luxor Temple's obelisks pierce the sky like frozen sunbeams, their rose granite surfaces carved with hieroglyphs that gleam under the Egyptian sun. These towering monuments, some standing 80 feet tall and weighing as much as 70 tons, weren't just decorative, they were cosmic bridges, believed to channel the sun god Ra's divine energy to Earth. But how did a civilization without steel or mechanized tools extract, transport, and erect these slender giants with such impossible precision? The answer lies in a marriage of brute force, hydrological genius, and an almost fanatical attention to detail. First came the quarrying. The granite for Luxor's obelisks was sourced from Aswan, over 100 miles up the Nile. Workers used dolerite hammerstones, a rock harder than granite, to pound trenches around the desired obelisk shape, deepening them daily until they reached the necessary depth of 30 feet or more. Then, under the watchful eyes of master architects, teams levered the monolith free using wooden beams, a delicate operation where one wrong move could fracture months of labor. But the real test began once the obelisk lay horizontal. Moving something so massive required more than muscle, it demanded physics. The Egyptians turned their greatest obstacle into their greatest ally, the Nile itself. During the annual flood, when waters swelled high enough to reach the quarry edges, workers loaded the obelisk onto a reinforced barge. Picture this: a vessel built from papyrus and acacia wood, lashed together with ropes thicker than a man's arm, groaning under the weight of a single stone slab. Teams would have stabilized the barge with counterweighted sides, letting the river's current carry the obelisk downstream toward Luxor. But here's the stroke of brilliance: they didn't fight the river's capriciousness. Instead, they timed the journey with the flood's recession, allowing the receding waters to deposit the barge near the temple site as naturally as a leaf settling on a pond. On land, the challenge grew exponentially. To move the obelisk from riverbank to foundation, workers constructed a lubricated slipway, a pathway of packed mud and clay, soaked with water to create a slick surface. Hundreds of laborers, chanting in unison, hauled the stone forward on wooden sledges, likely using a system of ropes and levers to inch it forward. Contemporary tomb paintings depict men pouring water ahead of the sledge, a trick that reduced friction to nearly zero, making the impossible merely arduous. Then came the heart-stopping moment, the raising. Unlike blocky pyramids, an obelisk's slender form made it perilously top-heavy. Archaeologists believe the Egyptians built massive earthen ramps beside a pre-dug pit, sliding the obelisk base first until its tip pointed skyward at a shallow angle. Then, using a combination of leverage and counterweights, possibly sandbags or smaller stones, they pulled it upright in stages, adjusting the supporting ropes millimeter by millimeter until it slotted perfectly into its waiting base. A single misjudgment could send the obelisk crashing, yet these engineers executed the maneuver with flawless consistency. But the true marvel wasn't just the engineering, it was the artistry. Every inch of these monoliths was polished with quartz abrasives until they reflected like mirrors, then inscribed with hieroglyphs so precise they've endured 35 centuries of wind and sand. The hieroglyphs weren't mere decoration, they were sacred contracts binding the pharaoh's name to the gods in eternal stone. Some obelisks were even capped with electrum, a shimmering gold-silver alloy to catch the first and last light of day, transforming them into literal beacons of divinity. Today, as shadows stretch across Luxor's surviving obelisk, its twin now standing in Paris Place de la Concorde, it's not the scale that astounds, it's the intimacy. Each chip mark, each glyph, whispers of hands that shaped stone not as conquerors but as collaborators. The Egyptians didn't just build monuments, they orchestrated a dialogue between earth, water, and sky, turning raw rock into sunlight-given form. And perhaps that's why, millennia later, we still tilt our heads upward, awestruck not just by what they made, but by the unwavering belief that drove them to try. Chichen Itza's El Castillo doesn't just dominate the Yucatan jungle, it dances with the cosmos. This stepped pyramid, built by the Maya over 1,000 years ago, is a celestial timekeeper carved in limestone, its 4 staircases totaling 365 steps to mirror the solar year. But the real magic happens during the equinoxes, when the setting sun casts triangular shadows slithering down the northern staircase, merging with stone serpent heads at the base to create the illusion of a feathered serpent descending from the heavens. This wasn't just architecture, it was astronomy in stone, a testament to the Maya's obsessive precision in tracking celestial movements without telescopes or written equations. Constructing such a perfect alignment required more than ritualistic fervor. It demanded back-breaking logistics. Every limestone block was quarried locally, hacked free using obsidian chisels and basalt hammers, then shaped with abrasives like sand and water until the edges fit flush. Without wheels or metal tools, workers hauled these multi-ton stones along ramps of compacted earth and wooden rollers, their progress measured in sweat-drenched inches. The pyramid's core isn't solid. It's a clever lattice of rubble-filled chambers, reducing weight while maintaining stability, an early example of lightweight construction principles we still use today. But the genius lies in the layers. El Castillo wasn't built in one campaign. It's a Russian nesting doll of earlier pyramids. Archaeologists have discovered at least 2 smaller structures buried within, each phase meticulously aligned to preserve the original astronomical calibrations. The final version features 91 steps on each side, plus the shared platform at the top, totaling the days in a solar year. Even the terraces are spaced to correspond with Maya calendrical cycles, a 3-dimensional almanac for agricultural and ceremonial schedules. During construction, the Maya likely used rudimentary plumb bobs and chord measurements to maintain perfect right angles, but their true secret was observation. For generations, priests tracked the sun's path from wooden observation platforms, marking solstices and equinoxes with notched stones. This empirical data directly informed the pyramid's orientation, ensuring those iconic shadow plays would occur with clockwork precision. Modern laser scans revealed deviations of less than half a degree, an accuracy rivaling modern astronomical instruments. The pyramid's acoustics add another layer of wonder. A clap at the base produces an echo mimicking the Quetzal bird, sacred to the Maya, while footsteps on the stairs resonate like falling rain, an auditory illusion suggesting the structure was designed as much for ritual performance as for celestial observation. Some researchers speculate the interior chambers, with their precise angles and ventilation shafts, functioned as resonance chambers to amplify chants or drumbeats during ceremonies. Standing before El Castillo today, you're not just seeing a pyramid, you're witnessing a civilization's dialogue with the universe. The Maya didn't build to impress with scale. They engineered to commune, to measure, to celebrate the cosmos' rhythms. And perhaps that's why, centuries after its builders vanished, the stone serpent still slithers down the steps every equinox, a ghostly reminder that the greatest monuments aren't just made of rock, but of time itself. Petra's Alcosne emerges from the rose-red cliffs like a mirage, a temple not built but revealed, as if the Nabateans simply pulled back a curtain of stone to expose its grandeur. Carved entirely by hand into the sheer face of Jordan's sandstone mountains, this 2,000-year-old masterpiece defies logic. Every column, every delicate floral motif, every urn perched precariously atop its facade was painstakingly chiseled from the top down, with no room for error. Unlike freestanding structures where mistakes could be hidden or repaired, here, each strike of the hammer was permanent. So how did these desert-dwelling traders, without iron tools or scaffolding, transform solid rock into a symphony of precision? The process began with meticulous planning. Before a single chip was struck, Nabatean architects likely sketched designs directly onto the cliff face using ochre pigments or charcoal, mapping out proportions with knotted ropes and plumb lines. Then came the brutal work of extraction. Teams of craftsmen dangled from hemp ropes, their feet braced against wooden platforms wedged into the rock. With nothing but bronze chisels and iron-headed picks, they carved downward in stages, removing material layer by layer like sculptors peeling back an onion. The sandstone's natural consistency played to their advantage, soft enough to carve when freshly exposed, but hardening upon contact with air into a surface that could withstand centuries of wind and rain. But Alcosne's true marvel lies in its ornamental complexity. The facade isn't flat. It's a three-dimensional tapestry of columns, pediments, and statues recessed into the rock with millimeter precision. To achieve this, artisans employed a technique called blocking out, roughing out the general shapes before refining details with smaller tools. The Corinthian capitals, swirling with acanthus leaves, were likely carved using templates pressed against the stone, guiding each chisel stroke. Even the urn atop the structure, once rumored to hold a pharaoh's treasure, was hollowed from the living rock, its interior space painstakingly excavated from behind. What's often overlooked is the engineering behind the artistry. The Nabateans carved drainage channels into the cliff above Al-Kosneh, diverting seasonal waterfalls away from the facade to prevent erosion. They also undercut the temple's base, creating a slight overhang that sheds rainwater like a gargoyle on a medieval cathedral. These weren't just aesthetic choices, they were calculated preservation tactics, ensuring the structure's survival in a region prone to flash floods. The cultural context deepens the wonder. Al-Kosneh wasn't just a temple, it was a billboard. Petra sat at the crossroads of ancient trade routes, and this flamboyant facade visible from the narrow Sikh Gorge approach served as a potent advertisement of Nabatean wealth and sophistication. The mix of architectural styles, Greek pediments, Egyptian cornices, Mesopotamian motifs wasn't accidental. It signaled to caravans from Rome, Persia, and Arabia that here was a city open to all, where diverse cultures converged under the Nabateans' skilled stewardship. Modern laser scans reveal something even more astonishing. The interior chambers align with celestial events. During the winter solstice, sunlight penetrates the inner sanctum, illuminating a rare niche where sacred rituals may have occurred. This fusion of astronomy, engineering, and artistry suggests the Nabateans weren't just mimicking grandeur. They were encoding their understanding of the cosmos into the very bones of the mountain. Standing in the Sikh at dawn, when the first light sets Al-Kosneh's facade ablaze in hues of crimson and gold, you realize this wasn't carving, it was alchemy. The Nabateans didn't move mountains, they convinced the mountain to reveal its hidden soul. And 2 millennia later, as shadows creep across those ancient columns, the stone still murmurs their secret. True mastery isn't about forcing nature to obey, but listening closely enough to hear what it's willing to surrender. The Great Wall of China winds across mountains and deserts like a dragon's spine, its brick and stone facade so iconic that generations believed it could be seen from space. But here's the truth, that's a myth. Even from low Earth orbit, the wall blends into the landscape, no more visible than a highway thread. The real wonder isn't visibility, it's how this colossal structure began as a patchwork of rammed earth and rubble over 2,000 years ago, long before bricks became its signature. Those earliest sections, built during the Qin dynasty, were feats of raw labor and ingenuity. Workers mixed local soil with gravel and water, then packed it between wooden frames layer by layer, pounding each stratum with logs until it hardened like concrete. No mortar, no fancy materials, just compacted earth that could withstand centuries. In the arid north, this rammed earth dried rock solid. In humid regions, builders reinforced it with layers of reeds or tamarisk branches for stability. Some stretches still stand today, worn but defiant, their surfaces pocked by time yet refusing to crumble. But how did they move those massive stones for later sections? Without cranes or carts, laborers relied on sheer numbers and clever physics. In mountainous areas, teams levered boulders up inclines using wooden sledges and rollers, while in flatlands, they transported materials along temporary roads paved with tree trunks. The wall wasn't built in one push, it grew organically, dynasty by dynasty, with each ruler adding new segments. Ming-era bricks, the ones we picture today, didn't appear until the 14th century, fired in kilns along the route and hauled by mule trains. What's often overlooked is the wall's adaptability. Builders didn't fight the terrain, they collaborated with it. Steep slopes became natural barriers, while valleys were plugged with watchtowers. In the Gobi Desert, where stone was scarce, they mixed sand with pebbles and bound it with sticky rice mortar, an ancient recipe so strong it outlasted empires. Even the walls' curves weren't arbitrary. They followed strategic sightlines, allowing sentries to spot smoke signals relayed from tower to tower. Modern engineers still marvel at the logistics. Estimates suggest millions of workers toiled over centuries, some conscripted as punishment, others volunteering for food during famines. The human cost was staggering, but the result was a living system, not just a barricade, but a highway for troops, a customs checkpoint for Silk Road traders, and a symbol of resilience. Today, as drones map eroded sections and archaeologists uncover hidden branches, the wall whispers its true lesson: greatness isn't about being seen from space. It's about the quiet determination to shape the earth itself into something enduring. Borobudur rises from the jungles of Java like a stone mandala brought to life, its 9 stacked terraces forming the world's largest Buddhist monument. Built in the 9th century from over 2 million volcanic stones, this colossal structure defies logic. Not a single drop of mortar holds it together. Yet after 1,200 years of monsoons and earthquakes, its intricate reliefs remain as crisp as the day they were carved. The secret lies in a system so elegant it borders on divine. Each block meticulously shaped to interlock with its neighbors like pieces of a 3-dimensional puzzle, their weight alone binding the entire edifice into an unshakable whole. The construction process was a symphony of coordination. Workers quarried andesite stone from nearby riverbeds, splitting slabs using nothing but wooden wedges and water. As the wedges swelled, they fractured the volcanic rock along clean lines, yielding blocks that could weigh up to 400 pounds. Transporting these stones to the hilltop site required a human chain stretching miles, teams passing rocks hand over hand, their rhythm as disciplined as a chanting monastery. Without wheels or pack animals, every ounce of progress relied on sheer muscle and communal effort. But the real magic happened during assembly. Each stone was dressed with grooves and protrusions, their edges beveled to create friction locks that prevented shifting. The builders didn't just stack, they engineered downward pressure, designing each tier slightly narrower than the one below, compressing the entire structure into a self-stabilizing mass. The precision was staggering. Curved walls were achieved by subtly tapering block heights, creating gentle arcs without a single misfit. Even the reliefs, 3,000 narrative panels and 500 Buddha statues, were carved in situ after placement, their flowing scenes spanning multiple stones yet appearing seamless. What's often overlooked is the hydrological genius. Borobudur's builders sculpted the hill itself into a natural drainage system, layering porous soils and gravel beneath the monument to channel rainwater away from the foundation. The temple's bell-shaped stupas aren't just decorative. Their lattice designs allow wind to pass through, reducing lateral pressure during storms. This wasn't just architecture, it was a dialogue with nature, where every stone listened to the whispers of wind and water. Today, as dawn mist clings to Borobudur's upper terraces, the monument still radiates its original purpose, not as a fortress or palace, but as a path to enlightenment. Pilgrims circle its levels in silent meditation, tracing the same routes builders once did, their footsteps echoing a truth carved deep into the stone. Greatness isn't built through force, but through the patient alignment of countless small perfections. Beneath the windswept plains of Cappadocia lies a secret that defies imagination during Kuyu, an entire city carved 18 stories deep into volcanic rock, sheltering up to 20,000 people for months at a time. While most ancient civilizations built upward, reaching for the sky, the people here burrowed downward, turning the earth itself into a fortress, and they did it all with nothing but simple hand tools. No electricity, no heavy machinery, just an extraordinary understanding of geology and survival. The city's layout reveals a brilliance born of necessity. Every corridor, stairway, and chamber was chiseled from soft volcanic tuff, a rock firm enough to hold its shape yet porous enough to carve with relative ease. Workers likely used basalt hammers and bronze picks to hollow out space inch by inch, their progress illuminated by flickering oil lamps. But Derinkuyu wasn't just a haphazard network of tunnels, it was meticulously planned. Circular doorways, some as narrow as waist height, acted as choke points against invaders, while massive rolling stone doors could seal entire levels in an instant. The engineering didn't stop at defense. Ventilation shafts, some plunging over 200 feet deep, ensured fresh air reached even the lowest levels, while wells tapped into underground rivers, providing water even during sieges. The city's true genius lies in its adaptability. Spaces weren't just carved, they were repurposed. Stables held livestock without wasting oxygen, their floors sloped to drain waste. Winemaking rooms featured fermentation pits, suggesting life underground wasn't just about survival but continuity. Communal kitchens shared heat through carefully placed vents, while chapels and schools kept society functioning. Some tunnels even stretched for miles, linking Derinkuyu to neighboring underground cities, a subterranean highway system for emergencies. What's most astonishing is the timeline. While the city reached its peak under Byzantine rule, evidence suggests it may have begun as early as the 8th century BCE, meaning generations expanded it over centuries, passing down techniques without blueprints or written records. Modern laser scans reveal previously hidden chambers still unexplored, hinting that even now, we've only scratched the surface of what lies beneath. Standing in one of Derinkuyu's dimly lit passages, you realize this wasn't just a refuge, it was a revolution in living. These builders didn't just hide from the world, they redefined it, proving that safety and community could thrive even in the belly of the earth. The stones don't whisper of fear, they hum with the quiet confidence of people who knew how to bend rock to their will. And perhaps that's the lesson echoing through these tunnels. True resilience isn't about fleeing the surface but mastering the depths. Ollantaytambo's stone walls loom over Peru's sacred valley like the unfinished work of giants. Massive blocks of rose rhyolite, some weighing over 50 tons, fitted together with seams so tight they defy the passage of centuries. This Inca fortress temple complex poses a riddle. How did a civilization without draft animals or iron tools move these megaliths from quarries high in the mountains, across a river, and up steep terraces to their final positions? The answer lies in a blend of geology, collective labor, and an almost superhuman understanding of stone's secrets. The journey began at the quarries of Cachicota, nearly 4 miles away and 2,000 feet above the construction site. Here, workers pried stones loose using bronze chisels and hammerstones, exploiting natural fractures in the volcanic rock, but extraction was the easy part. Transporting these behemoths required a feat of logistics that would challenge modern engineers. The Incas likely crafted a network of earthen ramps and inclined planes, lubricating the paths with mud to reduce friction as teams hauled stones on wooden sledges. Some researchers suggest they built temporary canals during the rainy season, floating the lighter blocks along diverted river currents, a technique hinted at by ancient grooves worn into bedrock near the riverbank. Once across the Yorubamba River, the real test began. To ascend Ollantaytambo's terraces, laborers may have used a system of counterweights and levers, anchoring ropes to stone protrusions still visible on the terraces today. The largest blocks, like the famed Wall of the Six Monoliths, were likely lifted incrementally, with workers building temporary earthen platforms beneath each stone to raise it step by step. The precision that followed was staggering. Each rhyolite block was painstakingly shaped by abrasion, rubbing stone against stone with sand and water until the surfaces matched perfectly. The result, walls where even the irregularly shaped blocks interlock like puzzle pieces, their undulating seams dispersing seismic energy during earthquakes. What's often overlooked is the social organization behind this effort. The Incas operated under a system called mitter, where communities contributed rotating labor as a form of tax. Thousands would have coordinated under master architects, their work synchronized like a human ant colony. The stones themselves tell this story. Some bear cryptic markings, possibly quarry identifiers or alignment cues, suggesting a sophisticated system of communication across teams who never shared a written language. The site's unfinished state offers rare clues. Scattered monoliths and partially carved blocks reveal the Incas' process. Stones were roughly shaped at the quarry, fine-tuned during transport, and perfected on site. One abandoned block near the quarries, nicknamed the Tired Stone, shows grooves where ropes once bit into its surface, a frozen moment in a journey that was never completed. Historians speculate that Ollantaytambo's construction halted abruptly during the Spanish conquest, leaving behind a snapshot of Inca ambition frozen in time. Standing before these walls today, you're left with a humbling realization. The Incas didn't just build a fortress, they engineered a conversation between mountain and monument, transforming raw stone into a testament of communal will. Every perfectly fitted block whispers the same truth. Greatness isn't measured by the tools you hold, but by the ingenuity with which you wield them. And perhaps that's why Ollantaytambo endures not as a ruin, but as a challenge, daring us to rethink what's possible when human hands and earthly materials conspire to outlast time itself. Karnak Temple Complex sprawls across the Nile's east bank like a stone forest frozen mid-sway, its towering columns thick as ancient oaks. This wasn't just a temple, it was a celestial machine built across 2,000 years by pharaohs competing to outdo their ancestors. At its heart stands the hypostyle hall, a labyrinth of 134 papyrus-shaped columns soaring 70 feet high, their capitals wide enough to hold 50 people. Imagine the din of construction when these giants were raised, thousands of workers chanting as they hauled sandstone blocks weighing up to 60 tons, their tools nothing more than copper chisels and limestone pounders. The secret to Karnak's construction lies in a combination of simple machines and staggering manpower. Teams would have dragged stones from quarries over 100 miles south, floating them downstream on barges during the Nile's annual flood. Once on site, laborers maneuvered blocks up earthen ramps packed with mud bricks, lubricating the slopes with water to reduce friction. For the tallest obelisks, some reaching 90 feet, engineers likely built massive sand pits around their bases, gradually removing sand to lower the monoliths into perfect vertical alignment. The precision beggars belief. The pink granite obelisk of Hatshepsut, still standing today, deviates from true vertical by less than 1 degree after 35 centuries. But Karnak's true innovation was modular construction. Pharaohs didn't demolish their predecessors' work, they built around and over it, creating a living archive of architectural evolution. Walls feature recycled blocks from earlier dynasties, their original carvings still visible inside later additions. This palimpsest of stone reveals how techniques improved over generations. Early columns have rough, irregular bases, while later ones interlock with mathematical precision. The entire complex functions like a three-dimensional timeline, where you can trace the development of Egyptian engineering by running your fingers along the stones. What truly sets Karnak apart is its cosmic alignment. The main axis points toward the winter solstice sunrise, when the first rays would pierce through the temple's innermost sanctuary to illuminate statues of the gods. Achieving this required not just astronomical knowledge, but an understanding of optics. Architects deliberately narrowed doorways along the processional route to create a focused beam of light. Even the hall's columns were spaced to allow sunlight to filter through at specific angles during religious festivals, turning stone into a sundial of the sacred. Modern laser scans have revealed hidden layers of complexity. Beneath the visible temple lie foundations packed with gravel and sand, an ancient seismic buffer that allowed the structure to sway slightly during earthquakes without crumbling. The columns themselves aren't solid. Their outer shells conceal rubble cores, reducing weight while maintaining structural integrity. These weren't just aesthetic choices, they were calculated survival strategies in a land plagued by Nile floods and tectonic shifts. Standing in the hypostyle hall at noon, when sunlight stripes the columns like a scribe's ruled papyrus, you realize Karnak wasn't built to impress mortals. Its scale was a dialogue with the divine, each stone placed in perfect balance between earth and sky. The labor wasn't just physical, it was devotional, 1,000 years of whispered prayers made manifest in sandstone and sweat. And perhaps that's why, even in ruin, these columns still feel alive, not as relics of the past, but as vessels of an ambition so vast it could only be measured in the weight of mountains and the patience of stars. The Temple of Jupiter at Baalbek doesn't just challenge our understanding of Roman engineering, it laughs in the face of it. Beneath its towering columns lies a foundation of 3 monstrous stones, each weighing nearly 1,000 tons, more than 2 fully loaded Boeing 747 jets. These megaliths, known as the Trilithon, were positioned 20 feet above ground with a precision that defies their staggering mass. How did an empire without hydraulic cranes or steel cables maneuver blocks so massive that modern engineers hesitate to attempt replicas? The answer may lie in a combination of Roman ingenuity, relentless manpower, and a willingness to treat physics as a loose suggestion. Start with the quarry half a mile from the temple site. Here, workers exploited the stone's natural weaknesses, hammering bronze-tipped wooden wedges into pre-cut fissures, then soaking them with water. As the wood expanded, it fractured the bedrock along clean lines, a technique still used today in some quarries, but freeing the stones was just the first act. Transporting them required a symphony of coordination. Unlike Egypt's flat deserts or the Inca's sloping ramps, Baalbek's terrain was uneven, forcing engineers to carve temporary roads from the living rock. Teams likely laid parallel tracks of greased wooden beams, rolling the stones atop them like a primitive railway. Olive oil or animal fat would have reduced friction, while teams of oxen, or possibly hundreds of enslaved laborers, pulled ropes woven from hemp, their collective strength turning impossibility into mere exhaustion. The real puzzle was the lift. Roman engineers were masters of the ramp, not just simple inclined planes, but spiraling earthen structures that wrapped around construction sites like snake coils. By building these ramps layer by layer with packed soil and rubble, they could gradually raise the Trilithon blocks to their final height. Each stone would have been dragged upward inch by agonizing inch, its progress controlled by a system of counterweights and winches. The risk was catastrophic. A slipping block could crush workers or shatter on impact. Yet the Romans executed this dance of mass and momentum with chilling precision. But here's the twist. Recent excavations revealed a 4th block, abandoned in the quarry. Dubbed the Stone of the Pregnant Woman, this 2,100-ton behemoth suggests the Romans aimed even higher, attempting to surpass the Trilithon scale before conceding to logistical limits. Its surface bears tool marks and lever points, a frozen blueprint of ambition interrupted. Modern attempts to move it using Roman-era techniques have failed spectacularly, proving that even history's greatest builders sometimes met their match. What's often overlooked is the cultural calculus behind this effort. These weren't just foundation stones, they were psychological warfare. In a region bristling with rival powers, the Trilithon scale was a statement, Rome's way of saying their gods and emperors dwarfed all others. The temple's podium wasn't just functional, it was a stage for imperial theater where architecture became propaganda. Standing before these stones today, you're left with a humbling realization. The Romans didn't just build temples, they engineered astonishment, bending the laws of physics to their will. And perhaps that's why, 2 millennia later, we still stare slack-jawed at the Trilithon, not because it defies explanation, but because it dares us to believe that human ingenuity, when fueled by enough determination, can move literal mountains. Chand Baori's steps plunge into the earth like a geometric illusion, a staggering cascade of 3,500 precisely carved stairs descending 13 stories into the Rajasthan desert. Built over 1,000 years ago, this isn't just a well, it's a subterranean cathedral to human ingenuity, where every step was calculated to harvest something as fleeting as a drop of water in one of the world's harshest climates. What's astonishing isn't just the scale, but the precision. Each stair is precisely aligned, creating a mesmerizing symmetry that funnels visitors downward into the cool, damp darkness where groundwater pooled like liquid gold. Carving this masterpiece required more than brute force. It demanded an intimate dance with the environment. Workers used nothing but simple iron chisels and hammers to chip away at the local volcanic rock, shaping steps so uniform they seem machined. But the true genius lies in the layout. The steps form a perfect inverted pyramid, narrowing as they descend to minimize evaporation while maximizing shade. This wasn't random, it was thermodynamics in stone. The deeper tiers stay up to 15 degrees cooler than the surface, creating a natural refrigeration effect where communities stored perishables during scorching summers. Even the placement was strategic. Chand Baori sits at the confluence of underground aquifers, its builders somehow mapping subterranean water flows without modern technology, likely by observing plant growth and seasonal fissures in the earth. The construction process would have been a marvel of coordination. Teams worked in shifts, beginning at dawn when the stone was coolest, their progress marked by ropes knotted at intervals to ensure step consistency. Without scaffolding, they carved from the top down, suspending themselves on hemp ropes as they chiseled deeper. The stair walls bear faint numerical markings, an ancient quality control system where master masons checked each tier's alignment against plumb lines made of weighted strings. What's often overlooked are the side chambers branching off the central staircase. These weren't just decorative, they functioned as air channels, funneling breezes downward to combat humidity and prevent mold, a passive ventilation system centuries ahead of its time. But Chand Baori's brilliance extends beyond engineering. This was a social hub, a sacred space, and a lifeline rolled into one. The narrow steps forced single-file movement, creating a natural queue during water collection, while shaded landings hosted impromptu markets and gossip sessions. At the base, a rectangular pool acted as both reservoir and ritual site, its still waters reflecting ornate carvings of Hindu deities that adorned the walls. During droughts, priests performed ceremonies here, their chants echoing off the honeycomb of steps as they appealed to the gods for rain. Modern hydrologists still puzzle over the well's efficiency. Even in years when nearby wells ran dry, Chand Baori's deepest recesses held water. The secret, a filtration system of porous stones and charcoal layers hidden beneath the lowest steps, purifying seepage from underground springs. Recent drone scans reveal something even more remarkable. The well's foundation isn't flat. It slopes imperceptibly toward one corner, creating a natural vortex that prevented stagnation by keeping water circulating. This level of hydrological sophistication, achieved with nothing but observation and trial and error, rivals modern groundwater management systems. Standing at the rim today, watching sunlight slice diagonally across the steps, you realize Chand Baori isn't just architecture, it's a dialogue between survival and artistry. Every stair tells the same story. That necessity doesn't just breed invention, it can elevate it to poetry. And perhaps that's why, after a millennium of monsoons and droughts, these steps still lead somewhere vital, not just to water, but to the very heart of what it means to adapt, to persist, and to carve order from the chaos of an unforgiving world. Great Zimbabwe's stone walls rise from the savannah like a puzzle where every piece locks into place by gravity alone. This medieval city, built between the 11th and 15th centuries, wasn't just a settlement, it was a testament to how granite, sweat, and ingenuity could shape an empire without a single drop of mortar. The walls, some reaching 30 feet high and up to 20 feet thick, curve and taper with a precision that defies their rugged material, their stones fitting so tightly that even after 7 centuries, you'd struggle to slide a blade between them. The secret lies in the rock itself. Zimbabwe's granite weathers naturally into rectangular blocks, splitting along clean lines that require minimal shaping. Builders exploited this, selecting stones that interlocked like jagged teeth, their irregular edges creating friction that mortar would only weaken. Teams of laborers, likely organized through a communal labor system called NHIM, would have transported these multi-ton blocks using log rollers and woven grass ropes, their progress measured in sun-scorched increments. But the real artistry came in the stacking. Each course was laid slightly recessed from the one below, creating walls that sloped inward as they rose. This wasn't just aesthetics, it stabilized the structure, distributing weight so effectively that even earthquakes couldn't topple them. What's often overlooked is the city's economic brilliance. Nestled between gold fields and Indian Ocean trade routes, Great Zimbabwe thrived as a commercial powerhouse. The walls weren't just fortifications, they were advertisements. Their imposing scale signaled wealth and stability to Swahili merchants arriving with glass beads from Persia or porcelain from China. Excavations reveal artifacts from as far away as Arabia, evidence of a trading network spanning continents. The very stone spoke a universal language, permanence. The construction methods reveal a society attuned to both practicality and symbolism. Circular enclosures mirrored traditional Shona village layouts, while the conical tower at the city's heart may have functioned as a granary or spiritual landmark, its precise purpose still debated. Modern laser scans show the walls align with solstice sunrises, suggesting celestial observation played a role in their orientation. Yet for all its sophistication, Great Zimbabwe required no written blueprints. Knowledge passed orally from master masons to apprentices, each generation refining techniques through touch and tradition. Perhaps the most humbling detail is what's missing, any sign of forced labor. Unlike the pyramids or Roman Colosseums built on the backs of enslaved workers, Great Zimbabwe's walls rose through collective effort. This was a society where building was communal, not coerced, a collaboration between earth and hands where every stone carried the weight of shared ambition. Today, as the wind whistles through the empty enclosures, the ruins don't whisper of conquest. They hum with the quiet certainty of people who knew how to make the land itself hold their dreams. The Leshan giant Buddha doesn't just sit. It emerges, an entire mountainside transformed into serenity. Towering 233 feet above the confluence of 3 rivers in China's Sichuan province, this colossal statue wasn't built, it was revealed, painstakingly freed from the cliff face over 9 decades of relentless labor. Unlike freestanding statues that rely on scaffolding and supports, every inch of the Buddha, from his coiled hair to his toes resting on the riverbank, was carved directly into the living rock, a subtraction rather than an addition. The process began in the year 713, when a monk named Haitong envisioned the statue as both a spiritual beacon and a practical solution. The rivers below were notorious for deadly whirlpools, and Haitong believed the Buddha's presence would calm the waters. His ambition bordered on madness, to carve a statue so massive that its big toe alone could seat a dozen people, using nothing but hand tools and fire. Workers started at the top, carving the head and shoulders first to minimize the risk of debris damaging finished sections below. They dangled from ropes anchored to the cliff, their chisels biting into the sandstone as they inched downward year after year. Heat played a surprising role. To fracture stubborn sections, teams built fires against the rock face, then doused the superheated stone with vinegar or cold water, causing thermal shock cracks that made carving easier. The debris was no accident either. Tons of fallen rock were deliberately dumped into the river to alter its flow, eventually taming the deadly currents just as Haitong had predicted. Detail was everything. The Buddha's coiled hair consists of 1,021 individual buns, each carved with the same precision as the folds of his robes. His ears stretched 23 feet long, hollowed out to reduce weight and prevent collapse. Even the drainage system was ingenious, hidden channels woven into the statue's back and arms divert rainwater away from the face, preventing erosion for over 12 centuries. Perhaps the most astonishing feature is the Buddha's gaze. His downcast eyes, each 11 feet wide, appear to follow viewers from any angle, an optical illusion achieved through meticulous calculation of their curvature and depth. Modern engineers have noted another subtle trick. The statue's posture leans slightly forward, counteracting the optical distortion that would make it appear to recede when viewed from below. When work finally ended in the year 803, the result wasn't just art, it was a masterclass in environmental engineering. The Buddha's presence stabilized the cliffs, while his shadow cooled the riverbanks, creating a microclimate where grasses took root in the once barren stone. Today, as tourists cluster on his massive feet like ants on a loaf of bread, the statue still radiates its original purpose, not just as a monument to faith, but as proof that patience and precision can carve order from chaos, one chisel strike at a time. Tikal's temple Roman 4 pierces the Guatemalan jungle like a stone spear thrown by the gods. The tallest structure in the pre-Columbian Americas, its stepped summit towering 212 feet above the rainforest canopy. What's astonishing isn't just its height, but the madness of its logistics. Every block of limestone, every pound of mortar, was hauled through tangled vines and suffocating humidity without wheels, metal tools, or even domesticated animals to shoulder the burden. This wasn't construction, it was a slow-motion battle against nature itself, won through sheer tenacity and an almost supernatural understanding of materials. Start with the stones. Workers quarried limestone from bedrock pits miles from the site, prying slabs loose with obsidian chisels and basalt hammers. Obsidian, a volcanic glass sharper than surgical steel when fractured, could make clean cuts in the soft limestone, but it shattered easily, requiring constant replacement. Teams would have stockpiled thousands of these tools, their edges dulling after just minutes of use. Once freed, the multi-ton blocks faced a gauntlet of mud and roots. The Maya didn't just drag them, they floated them. During the rainy season, workers laid down corduroy roads, woven mats of branches and palm fronds to keep sledges from sinking into the muck. Some archaeologists believe they even diverted seasonal streams, creating makeshift canals to ferry stones partway on rafts made of buoyant cedar wood. The real genius lay in the mortar. Unlike the mortar we know today, Maya lime plaster was a centuries-old science. Workers burned limestone in kilns at temperatures exceeding 1,600 degrees Fahrenheit, then slaked the resulting quicklime with water and tree sap to create a paste that hardened into something stronger than the original rock. This wasn't just glue, it was alchemy. The sap acted as a natural polymer, making the plaster flexible enough to withstand earthquakes yet durable enough to survive a millennium of tropical downpours. And they made thousands of tons of it. Temple Roman 4 core isn't solid stone. It's a honeycomb of rubble-filled chambers bound together by this mortar, reducing weight while maintaining structural integrity, an ancient precursor to modern lightweight concrete techniques. But how did they lift those stones 200 feet into the air? The answer lies in the temple's own design. The Maya built incrementally, erecting a series of ever smaller platforms atop each other like stacking boxes. Each tier served as a work platform for the next, with ramps of compacted earth and wooden scaffolding allowing laborers to hoist materials higher. Unlike Egyptian pyramids where ramps spiraled around the exterior, Maya ramps likely zigzagged up the temple's sides, their angles calculated to distribute the weight of dragged stones without collapsing. Workers would have used log rollers and woven hemp ropes, their collective strength amplified by simple machines like levers and fulcrums. And here's the kicker, they did it all while accounting for the jungle's unstable soil. The temple's base is wider than its peak, its walls angled inward to counteract settling, a technique modern engineers call batter. The pyramid's alignment reveals another layer of sophistication. Temple Roman 4 doesn't just point north, it's angled to frame the rising sun during the winter solstice, when the sun's first rays would ignite the temple's crest in a blaze of gold. Achieving this required naked eye astronomy so precise that modern surveys using GPS have confirmed its alignment to within a fraction of a degree. Priests likely used paired observation points, smaller temples or stone markers, to track celestial movements over generations, embedding that knowledge into the very bones of the structure. What's often overlooked is the human symphony behind this effort. Tikal wasn't built by slaves but by a mobilized citizenry, where labor was a communal duty woven into the fabric of society. The mortar mixes bear fingerprints of countless workers. Some stones even bear glyphs thought to mark the work crews who placed them. This wasn't just a temple, it was a societal project, a collective act of devotion that bound the city together. Standing atop Temple Roman 4 today, gazing over an endless green ocean of treetops, you realize the Maya didn't just conquer the jungle, they conversed with it. Every stone, every ounce of mortar whispers a truth we're only now rediscovering. That true innovation isn't about forcing nature to yield, but learning to hear its rhythms and build in harmony with them. The temple doesn't just stand against time, it dances with it, a monument not to human dominance but to human patience. And perhaps that's why, centuries after its builders vanished, the stones still hum with their presence. Beneath the sun-baked streets of modern Malta lies a labyrinth of tunnels and chambers so acoustically perfect, it feels less like an archaeological site and more like a cathedral carved by sound itself. The Hypogeum of Hal Saflieni, a subterranean temple complex dating back over 5,000 years, wasn't just dug into the limestone, it was sung into existence. With nothing but flint tools and obsidian scrapers, Neolithic builders hollowed out 3 levels of interconnected chambers, some painted in ochre swirls that still cling to the ceilings like ancient graffiti. But what truly chills the spine isn't the artistry, it's the acoustics. Certain rooms resonate at precisely 110 Hz, a frequency known to alter brain activity, inducing trance-like states in those who hear it. Was this coincidence, or were these chambers designed as sonic temples where ritual and resonance merged into something transcendent? The construction defies logic. Working in near darkness, lit only by flickering oil lamps, teams chiseled downward from a single entry point, removing an estimated 2,000 tons of stone without written plans or measuring tools. The walls bear the marks of their tools, zigzagging grooves where flint saws sliced through the soft Globigerina limestone, while harder strata were painstakingly pecked away with stone picks. But precision wasn't sacrificed for speed. Doorways align with solstice sunrises, funneling beams of light to specific niches during key dates in the agricultural calendar. The so-called oracle chamber takes this further, a small niche carved at face height where spoken words reverberate through the entire complex, their echoes lingering for an unnatural 12 seconds. Modern sound engineers have confirmed the effect. The chamber's elliptical shape and concave walls create standing waves that amplify certain frequencies while dampening others, a feat of psychoacoustics we'd struggle to replicate even with computer modeling. Then there's the art, faded but still haunting. The ceiling of the main chamber swirls with spirals and honeycomb patterns in red ochre, their pigments mixed with animal fat to endure millennia. Some reliefs depict corpulent figures, goddesses or ancestors, their forms echoing the rounded contours of the walls themselves. But the most unsettling discoveries weren't on the walls, they were beneath the floors. Excavations revealed the bones of over 7,000 individuals, layered like strata in a sacred geology. Skulls showed deliberate deformation, their flattened crowns hinting at a culture that shaped minds as carefully as they shaped stone. The hypogeum's purpose remains a riddle wrapped in silence. Was it a necropolis, a ritual space, or something more primal, a womb of the earth where the living communed with the echoes of the dead? The answer might lie in the very stones, Recent laser scans have revealed previously hidden chambers, their entrances sealed with deliberate care. Whatever secrets they guard, one truth is inescapable: this wasn't just dug. It was composed, a symphony in stone and sound that whispers across 5,000 years, not with answers but with a question: how did they know? How did Neolithic hands, guided only by firelight and intuition, engineer spaces that still hum with uncanny power? The hypogeum doesn't just defy time, it defies our assumptions about what ancient people understood and what they could hear in the dark. Rising from the ancient plains of the West Bank, the Tower of Jericho stands as a silent sentinel of human ambition, a staggering stone structure built 8,000 years before the pyramids of Egypt cast their shadows over the desert. This conical tower, nearly 30 feet tall and constructed with nothing but stone tools and communal labor, is more than just the oldest known monumental building. It's a riddle wrapped in layers of time. Its walls, built from undressed stones carefully fitted together without mortar, curve inward as they rise, a deliberate design choice that hints at an understanding of stability long before the term engineering existed. What's truly baffling isn't just the tower's age, but its purpose. Unlike later defensive towers with arrow slits or battlements, Jericho's structure lacks obvious military features. Instead, its interior holds a secret: a steep, winding staircase spiraling 22 steps into darkness, wide enough for only one person to ascend at a time. Was this a watchtower guarding against invaders, or something more mystical? Some archaeologists point to its alignment with the summer solstice sunrise during the longest day of the year. The first rays would have illuminated the stairway's entrance like a beacon. Others argue the tower anchored ritual ceremonies, its height lifting participants closer to the heavens in a town already famous for its circular dwellings and skull cult practices. The construction process itself defies expectations. Workers quarried local limestone using flint chisels and fire setting, heating rocks with fire, then dousing them with water to fracture the stone. Without wheels or pulleys, they likely dragged blocks on log rollers, leveraging the slope of the surrounding tell, a man-made mound to reduce effort. The tower's base sits atop a natural spring, suggesting its builders may have viewed the site as sacred long before the first stone was laid. Modern experiments show that lifting each stone into place would have required teams of laborers chanting in unison, their rhythm as much a part of the architecture as the rocks themselves. What's often overlooked is the social innovation behind this project. Erecting such a structure in 7,500 BC demanded more than brute strength. It required a level of social organization previously unseen. Someone had to coordinate food for workers, allocate tasks, and sustain the vision across generations. The tower's existence implies a society capable of deferred gratification, where short-term survival yielded to long-term collective ambition. Today, as desert winds whisper through the tower's eroded stones, it challenges our assumptions about prehistory. This wasn't built by a primitive people. It was engineered by innovators who turned rock and sweat into a testament of what humans can achieve when they dare to build higher than the horizon. And perhaps that's its enduring power, not as a relic but as a mirror, reflecting our own restless drive to reach beyond what seems possible. Nan Madol rises from the turquoise waters of Micronesia like a ghost city, its black basalt logs stacked into fortress-like walls that defy both the ocean's fury and conventional logic. This ancient metropolis, built atop a coral reef 1,200 years ago, consists of nearly 100 artificial islets separated by canals, earning it the nickname Venice of the Pacific. But here's what makes it truly astonishing. Every colossal stone, some weighing up to 50 tons, was quarried from volcanic cliffs across the island, then transported 25 miles over open water without metal tools, wheels, or even pulleys. The logistics boggle the mind. How did a civilization without draft animals or advanced machinery orchestrate such a feat? The answer lies in a combination of tidal ingenuity and backbreaking labor. Nan Madol's builders, the Sordelor dynasty, relied on the ocean itself as their conveyor belt. During high tide, they likely lashed basalt, logs, and prismatic columns formed by cooling lava to outrigger canoes or bamboo rafts, floating them along coastal currents to the construction site. At low tide, when waters receded, teams maneuvered the stones onto wooden sledges, dragging them across the reef's exposed surface using ropes woven from coconut fiber. The coral foundation wasn't just a challenge, it became part of the solution. Workers packed rubble and shells between the reef's natural crevices, creating stable platforms that prevented the heavy structures from sinking into the soft substrate. But the real genius is in the stacking. The Sordelor employed a crisscross technique, alternating the direction of each layer like log cabins, distributing weight so effectively that these walls have withstood centuries of typhoons. Some islets feature double-walled designs with interior fill, an early form of load-bearing construction that stabilized the structures against tidal erosion. The precision is haunting. Basalt columns fit together with gaps of less than an inch, their irregular shapes interlocking like puzzle pieces without mortar. Modern engineers speculate that builders used coral sand as a natural leveling agent, sprinkling it between stones to fine-tune their alignment before settling them into place. What's often overlooked is Nan Madol's celestial blueprint. The city's main axis aligns with the rising sun during the summer solstice, while certain islets cluster in patterns mirroring the constellation Orion. This wasn't just urban planning, it was cosmology carved in stone. The largest islet, Nandowas, houses a temple complex with walls 16 feet high, its entrance positioned so that the equinox sunrise illuminates the inner sanctuary. How did they achieve such accuracy without compasses or written records? Oral traditions hint at a system of navigation sticks and star maps where knowledge passed through chants and sand drawings. The societal implications are equally staggering. Nan Madol required an estimated 750,000 tons of basalt, a volume suggesting centuries of coordinated labor. Unlike slave-driven projects like the pyramids, evidence points to a collective effort where islanders rotated construction duties around agricultural cycles. Coral cores reveal something even more remarkable. The city's canals were engineered to flush with tidal currents, preventing stagnation and controlling fish breeding, a feat of ecological engineering that sustained its population for generations. Today, as mangrove roots snake through abandoned walls, Nan Madol whispers a paradox. Its builders mastered stone and sea with nothing but observation and patience, yet their descendants recall legends of the city's construction being aided by magic. Perhaps that's the point. When human ingenuity reaches such heights, it becomes indistinguishable from the divine. The stones don't just stand as ruins, they float, suspended between myth and reality, challenging us to rethink where technology ends and wonder begins. From the mathematical perfection of the Great Pyramid to the gravity-defying walls of Sacsayhuaman, these 30 ancient megastructures stand as silent witnesses to human creativity on an unimaginable scale. Each one tells the same extraordinary story, that civilizations long before cranes, computers, or even written language achieved what we'd struggle to replicate today. The Incas moved mountains of stone with nothing but rope and patience. The Maya tracked celestial movements using temples as their calculators. The Nabateans convinced cliffs to become palaces through sheer artistry. These weren't just buildings, they were acts of faith in what human hands could accomplish. What's humbling isn't just the scale, it's the diversity of solutions. The Romans mastered concrete that grows stronger with time, while the Khmer floated sandstone blocks down monsoon-swollen rivers. On Easter Island, a society in isolation engineered colossal statues. In Malta, Neolithic builders composed subterranean symphonies in stone. Every culture faced unique challenges: desert heat, jungle downpours, earthquake zones, and responded with innovations that still leave engineers in awe. The common thread, an unwavering belief that no obstacle was insurmountable when generations worked toward a shared vision. Yet for all we've uncovered, these structures guard their deepest secrets. How did the builders of Göbekli Tepe align their pillars with stars 12,000 years before telescopes? What precise acoustical knowledge shaped the hypogeum's trance-inducing chambers? The more we study these sites, the more we realize our ancestors may have possessed techniques lost to time, methods so effective they've outlasted empires, languages, even the memories of who built them. So here's a question to carry forward. If they could achieve so much with so little, what does that say about human potential? These stones don't just mark graves of the past, they're signposts pointing toward futures we've yet to imagine. Now it's your turn. Which of these ancient marvels speaks to you most? Is it the cosmic precision of Chichen Itza or the raw determination etched into Darinkuyu's tunnels? Share your favorite in the comments, and if you're hungry for more mysteries carved in stone, hit subscribe. The past isn't finished surprising us, and neither are